Tamam, başlayabiliriz. Okay, let's continue. So let's remember what we were doing last time. Let me see if I'm recording this. Yes. Okay. So last time we started this new chapter about linear transformations. So what is a linear transformation? So linear transformation is basically it's a function between two vector spaces. Okay, since vector spaces are sets, we can define functions between them. The important thing is linear transformation is not just a simple function, but it has certain properties. It has this property A and B. Basically, what it says is linear transformation respects vector addition. What do I mean by that? I mean that if I add two vectors and take its linear transformation, then I get the same thing as first applying this transformation to these vectors separately and then adding them. Okay, and the same thing is true for this scalar product. So if you remember that there are two operations on a vector space, vector addition and vector and scalar product. So in a sense, this linear transformation is preserving the vector addition and scalar product between these vector spaces. Okay, so then we looked at certain examples. For example, a linear transformation which is defined by this matrix vector product in R2 is a linear transformation. Okay, and this can be generalized in fact to an arbitrary m by n matrix. Okay, in this case we have this the vector the L defined by this product is in fact it's a linear transformation. And then we looked at some examples. For example, we can define a linear transformation from the polynomials into usual vectors, okay, like this, and this is a linear transformation. We showed this. Then we looked at a special example, and in this case, it's taking three vectors and it's sending it to two vectors. We checked whether this is a linear transformation, and we found that the answer is no. So this extra term plus one is making this transformation not linear. Okay, so we sometimes call this as nonlinear transformation. So this is example of a nonlinear transformation. And another example where it's not a linear transformation is when we have this vector x component is squared. Okay, so this is not a linear transformation. In a sense, we see which types of things are linear transformations. So this square here, this square term here is making this not a linear transformation. And if there was something like, I don't know, sine of x or cosine of x or e to the power x or x cubed or x times y, things like this make this a nonlinear transformation. Okay, it's not a linear. Those things are not linear transformations. So you should be able to tell what is a linear transformation just by looking at it. Okay. So this example, so this is from polynomials to polynomials, but polynomials of degree 1 to degree 2, and this is a linear transformation. We checked this one. And the final thing, we stopped here yesterday. We said that if we have a linear transformation, then the linear transformation must carry the zero vector in the first vector space to the zero vector in the second vector space. And this property also holds. So this is not true only for plus, or this also holds for minus. Okay, I said the proof of this one is easy. Let me show you how one can argue about the proof here. So maybe we have this date. What is the date? Is 5. So what is the proof of this? The proof is really easy. So proof works like this. So L of the 0 vector plus the 0 vector. So let me cut this. So what is this? What happens if I add two 0 vectors? I know that 0 plus 0 is 0. So this is basically the same thing as L of 0 vector, right? Because if I add two 0 vectors, then sum of 0 vectors is a 0 vector. So, but by linearity property, I can separate this into two parts. This also must be true because of linear transformation property. Now let's see what we have. We see that here we have some quantity here, some vector, and it equals, so what is this thing? Let me write one more step. What is this thing? So this is 2 times L of 0 vector. So a vector equals 2 times itself. So from here, we can either take this this part to the other side, and we can see that this vector must be the 0 vector, okay? So this implies L of 0 vector must be the 0 vector, but this time 0 vector on the right, the other vector space, W vector space, okay? Okay, this was the proof. This is an important property. So let's see some examples. So sometimes we can just use this property to see that a given example is not a linear transformation. For example, let's look at this one example. So suppose we have L is a mapping from R2 to R3. Okay. In this case, let's define L as Lxy equals x plus 1, y plus x, and z times x, okay, something like this. Then the question is same, is L a linear transformation? Let's look at the answer. So we just need to, like for this one, it's enough to check that 0 vector, the image of 0 vector. So if I take x and y to be 0, what do I get? I get 1, 0, and 0, right? 1, 0, 0. So this shows what? This shows L of the 0 vector of R squared, okay? So 2 zeros like this is not equal to 0 vector in R cube, 0, 0, 0. This shows that this transformation is not linear, okay? Okay, so this is a you see useful property. On the other hand, I want to stress that if this thing was the 0 vector on the right hand side, it doesn't mean that it's a linear transformation. Okay, so if these are not equal, then it's necessarily Z nereden geldi? Z'yi ben uydurmuşum. Z'yi de şey diyelim. Y çarpı x diyelim. Çok güzel. Tamam. So what was I saying? Yeah, so if it's not equal, this is not equal, then it's not a linear transformation. But if it is equal, then we can say it's a linear transformation, okay? So one example was this one. Where is it? Okay, let's look at it. So let's look, if I put 0 here, I get 0. So this carries the 0 vector to the 0 vector, but it's still not a linear transformation, okay? That's an important point. Okay. Now let's look at this example. So what is this example? So let's consider this linear transformation from R2 to R2. This time we are given that this is a linear transformation. Okay, so suppose that this is a linear transformation. And moreover, suppose that we know L of 1, 1 equals 1 and minus 2. And L of minus 1 and 1 equals 2 and 3. So what is the question? So the first part is this: find L of minus 1 and 5. Okay, so we are given L of two vectors. L11 is this guy, L minus 11 is this guy. Okay, so it's asking what is L of this vector. Okay, how do we find this? Now the way to do is this way. We will use, of course, the linear property, okay? Linearity property. So let's first try to write this vector minus 1 and 5 in terms of, let's call this A times 1, 1 plus B times minus 1 and 1. Okay, so let's try to find A and B such that this equation holds true, okay? Let's see if this equation has a solution. So the first component is A minus B. This must be minus 1. And the second component is A plus B. This must be 5. Okay, so from here, if I add these two equations, I get what? I get A equals 2A equals 4. So A must be 2 and B must be 3. So that's good. Oops. That's good. So what did we find? We found this one. So the thing we are trying to find is L of minus 1 and 5. Okay, this is the thing that we are trying to compute. We know that minus 1 and 5, the vector minus 1, 5, can be written as 2 times 1, 1 plus 3 times minus 1, 1. Okay, we showed this. So now is the crucial part. Now I will use the linear property. So I can separate this into, so this is a sum of two vectors. Okay, so by linearity property, I can write this as 2 times 1, 1 plus L of 3 times minus 1, 1. Okay, so here we use the property that I can separate sum into sums, right? So this is the linearity property. So now I want to take these oops. So I want to take this scalar products outside. I can also do this by linearity property. Okay, so this means this is 2 times L of 1, 1 plus 3 times, I can also take this 3 out. I can take this 3 out. So this gives me 3 times L of minus 1, 1. Okay, now we see why I did this. Now we can see why I did this. Why did I do this? Because I know the value of L11 and I know the value of L minus 11. So I know these values. I can just plug them here. Okay, so what is this? Let's write. So this is 2 times the vector 1 minus 2 plus 3 times the vector 2 and 3, right? So I can just compute this. So this is 2 plus 6, which is 8, and minus 4 plus 9 is 5. So the answer is 8 and 5. Any question? Okay, no questions. Now let's look at the other part. Part B is it's asking this time not just specific vector, but we want to find this for any x and y. So what is L of xy? So can we find the general formula of L just by knowing two values of it? Okay, so we know two values of it. We are given two values of it. Can we find the general formula for this? Okay, we know that this is usually not possible for arbitrary functions, right? Because if we just know, for example, if I draw a function like this, so if I just know these two values, right? That there will be infinitely many functions passing from just these two values. I cannot find the general formula for the function passing from just 2 points. But it turns out that for linear transformations, I mean for between R2 and R2, it turns out that it's sufficient to know the value of the function at just two values. If you know that, you know the value of the function at any value. Okay, that's interesting. So this linearity property is a very strong property. It's showing that. So how does this work? Okay, this time, so this is, what is this? So this time I will repeat myself, okay? So instead of this, I want to find A and B for arbitrary vectors. Okay, good. So let's write the same equations. This time A minus B is X and A plus B is Y. This means what? This means A is X plus Y over 2 and B is, what is B? Y minus X over 2, right? Very good. So let's try to compute L of x phi now. What is this thing? So this is L of A is x plus y over 2 times the vector 1, 1 plus y minus x over 2, the vector minus 1, 1. Very good. Now I can take these constant terms, these guys, outside. So I will repeat the same thing, but I will shorten my writing. So I get this value, x plus y divided by 2 of L11 plus y minus x over 2 L minus 1, 1. Okay, so let's write it here. So what was L11? L11, if you remember, it was this vector 1 and minus 2, and plus the second guy, y minus x divided by 2. What is L minus 1, 1? It looks like it is 2 and 3. Okay, I will check these things. So what is the final result? Final result is this one. So this is x plus y over 2, and then 2 times plus 2y minus 2x divided by 2. This is the first component, and the second component is minus 2x minus 2y, and then plus 3y minus 3x divided by 2. So what do we get? We get, what do we get? So minus x plus 3y over 2. And here, what is this? Minus 5x plus y over 2. Okay? Any questions here? Eksi x eksi y olacak. Bir saniye. İkinci kolumun başı. Pardon. Ne demek istediğin? Yanlış mı yapmışız? Doğru mu yani? Okay, we can check whether this is correct or not. So let's plug in these values. Let's plug in minus 1 and 5 here. And let's check if it gives 8 and 5, okay? L minus 1 and 5, is it, what is this? So if you use our formula, this will give us what? 1 plus 15 over 2. And then it will give us 5 plus 5 over 2. So this is 8 and 5. Just like what we found here, right? So it cannot be a coincidence. So I think the answer is correct. Any questions here about this example? Okay, so I want to show you the properties of these, like geometric properties of these linear transformations on R square, okay? So I should write verify here. For example, let's take, so we will look at vectors from linear transformations from R2 to R2. Let's consider some simple examples. For example, let's consider this xy. It takes a vector xy and it sends it to itself. So how does this work? So this is basically what this transformation is doing is it's taking it's sending so it's sending each vector to itself, right? So for example, if I take like a square here, it will, this map will do what? This map will take it to the same square, right? This is like the identity linear transformation. So let's consider something else. Let's consider, for example, let's take x and y, and suppose, so it sends it to 2x and y. So how does this transformation work? So I won't draw this left part, but just the right part. So how does this transformation work? Let's draw it. No. No. Okay. Maybe just here, right? Okay, this is good. So what does this transformation do, guys? So if I take this square, it takes this vector and this vector to which vector? So it takes, so suppose this is the unit vector. So this is 1, and this is also 1. So this is the 1 0 vector, and the other is the 0 1 vector. So it will take the 1 0 vector to 2 0, right? So it will increase its length by 2, and it will send 0 1 to 0 1. So what this transformation is doing is increasing the length in x by 2. So each length is increased by 2 in the x direction. So this is 2, and this is 1. Okay. So that's it. Let's look at another transformation. For example, suppose it takes x and y, and it sends it to x and minus y. So how does this transformation work? So this transformation, what this is doing is, so this time it will take this square, and what will it do? It will so if I take 1 0 vector, it will go to 1 0, but if I take 0 1 vector, it will go to 0 minus 1. So it's basically flipping the regions, right? So this time this vector takes that square and sends it into this square. So it's minus 1, and this is 1. So the image of a square here is flipped with respect to x-axis. Okay, this is the x-axis, this is the y-axis. Any questions? And if I take something a little bit more complicated, so let's take x and y. So what is this doing? So suppose that this is x plus y, and let's take it as y. What do you guys, this one will do? Let's look at it. Okay, this time it's taking the 1 0 vector to where? So 1 0 vector is sent to 1 0, right? So 1 0 is sent to 1 0. What about 0 1? The vector 0 1 is sent to 1 1. What is the 1 1 vector? 1 1 vector is this guy. So basically, what this transformation is doing is making that square a parallelogram. Okay, paralel kenar. So this is the vector. This is the vector. Let me write small here. This is the 1 1 vector, and this is the vector 1 and 0. Okay, so it's taking these vectors, these two vectors here, 1 0 and 0 1, into these vectors. Okay, so the image of the square is transformed to a parallelogram in R2, these two vectors. Okay, so you see these linear transformations can be like very useful for computer graphics and things like that. So for like working with there's some graphics software which works with like vector-based images, right? So you transform in those things. Vectors play the major role, and linear transformations are just transforming those vectors to other vectors. So you can easily generate new shapes. Okay. Okay, maybe I will give you one more example. This example is, let's consider this one. So what is the image of this vector? So it takes x to x and xy to x and 0. So what is the image of this square? What is the image of this square? Now, 1 0 vector is sent to 1 0, but 0 1 vector, 0 1 vector is sent to 0 0. Okay, so in fact, this vector does this. Let's see. So the image of that square is, this time it's just a line. Okay, so the image becomes the line. Just this vector, just 1 0, because the vector 0 1 is sent to 0 0. So yeah. So if you take any vector here like this, its image will be what? Its image will be this vector, just this part. Okay, because it only conserves its x component, so it will be sent to this vector. So all the vectors inside this square, they will be compressed to this line. Okay, this has very like a, this really has a relation with determinant. Okay, in a sense, all of these transformations that I have written, the first four ones, they have non-zero determinant. They are non-singular. Okay, I will talk about it as next thing. So you see, for example, the first one has determinant 1. Okay, this one has determinant 1. So it's in a sense both preserving the volumes or the areas. Okay, so this square has area 1 and this square has area 1. So it's preserving the area, and it's also preserving the orientation of the vectors. Okay, what about the second one? Second one has determinant 2. It's it's making this unit square into a rectangle with area 2. Okay, the third one has determinant -1. Okay, so it's preserving the area, but it's not preserving the orientation, the order of the vectors. So it's that flip is making the determinant -1. And this one has also determined positive determinant, so I don't know what the area is. We can see, right? So what is the area? So it's the 1 times the height, 1. So it's 1 times 1, right? What is the, I'm sorry, what is the what is the area of the parallelogram? Neydi arkadaşlar bu paralel kenarın şeyi? Şu uzunluk 1 ise, burası da 1 ise. it's 1 times 1, right? So it's still 1. So it's determinant is still 1, okay? But the last one has determinant 0. Okay, the last one has determinant 0. It's making the whole square, it compresses it into a single line which has 0 area. Okay, so now let's see what I mean by determinant of a linear transformation. Okay, so that's the next thing. Okay, so let's talk about this. Let's take a linear transformation between Rn to Rm. Okay, so let's consider this a linear transformation. And let's take the natural basis. So, or standard basis. What is the natural or the standard basis? Standard basis. Sometimes we call this natural basis. So natural basis is, the first one is 1, 0, 0, 0, 0. The second one is 0, 1, 0, 0, 0, 0. The third one is 0, 0, 1, 0, 0, 0. Okay, the standard. So if it was R cube, like it will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Those vectors are the natural basis. Okay. So let also A let A be the matrix whose jth column is L of EJ. Okay. Then we have this. Then L of X is the same as AX for every X in Rn. And this matrix A the standard matrix representation of the linear operator L. So what do we do now? Let's make this highlight. So standard matrix representation. Okay, so this is the important term here. Let me choose this one. Okay, so let's see for some examples. So let's look at here, maybe. So let's see the standard matrix representations of these linear transformations. So what is the matrix representation of this first one? So A is basically the matrix which is this L1, 0, the first column, and the second column is L0, 1. Okay, so L1, 0 is what? L1, 0 is 1 and 0, right? Because L takes 1, 0 to 1, 0 for this example. And L takes 0, 1 to 0, 1. So this is basically the identity matrix. How did we show this? We showed this by big I, right? So identity matrix. So this linear transformation is really the identity transformation. What about the second one? What is A for the second one? So all we have to do is look at the image of the vector 1, 0. The image of 1, 0 is 2, 0, and the image of 0, 1 is 0, 1. So this matrix is 2, 1, 2, 0, 0, 1. So its determinant is really 2. So that was what I wanted to say. Okay. And what about the third one? What about the third one? For the third one, what is the matrix representation? So here, let's write a matrix, a standard matrix representation here. Standard matrix representation. Okay, so what is A here? What is the image of 1 and 0? 1 and 0, it's 1 and 0. The image of 1 and 0 is 1 and 0. The image of 0, 1 is 0 and minus 1. Okay, so its determinant is minus 1. What about this one? This one, the image of 1, 0 is 1 and 0. The image of 0, 1 is 1 and 1. Okay, you see the determinant of this guy is also 1, as we found out. Finally, the last example, the standard matrix of this transformation is 1, 0 is sent to 1, 0, and 0, 1 is sent to 0, 0. Okay, so this is the standard matrix representation. Okay, so let's find a little bit more complicated example. So let me make this red. Okay, so this time let's consider a transformation from R3 to R2. And let it be defined as this. X, Y, and Z is transformed into X plus Y, X plus 2Y, and 3Y minus 2Z, okay? So this is transformation from R3 to R2. The question is find the standard matrix representation of this transformation. Okay. How do we do it? So A is basically the first column will be L of E1. The second column is L of E2, and the third column is L of E3. What is E1, E2, E3? They are the standard basis vectors. E1 is basically 1, 0, 0. So if I put 1, 0, 0 here, I get 1 for the first component and 0 for the second component, right? If I put x equals 1, y equals 0, and z equals 0, I get this one. If I put 0, 1, 0, I get 2 and 3. And if I put 0, 0, 1, I get 0 and minus 2. Okay? So maybe I should write what E1, E2, E3 is. So these are the standard basis vectors. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, this is the standard matrix representation. And let's do one more example and then finish. Okay, let's look at L from P1 to P1. Okay, so what is P1? So these are polynomial spaces, right? So suppose that this is a linear transformation. And suppose we know L of t plus 1 which is 2t plus 3, and L of t minus 1. And suppose this is 3t minus 2. The question is find L of 6t plus 6t minus 4. Okay, let's look at it. So we did a similar problem. So this will be the solution is just like that. So what we do is we represent the unknown vector 60. I mean the 60 minus 4 vector or 60 minus 4 polynomial as a combination of these two given polynomials, t plus 1 and plus b times t minus 1. So what does this give us? So this gives us a plus b must be 6 and a minus b must be minus 4. Okay, so a must be 1 and b must be minus b must be 5, right? B must be 5. Then we get L 60 minus 4 as L of 1 times t plus 1 plus 5 times t minus 1. Oops. Which gives LT plus 1 plus 5 times L t minus 1. Okay. So what is this? What is LT plus 1? This is 2t plus 3. What is LT minus 1? This is 5 times 3t minus 2. Okay, so the result is 17t and plus 1. Okay, guys. I think this is it's about the linear transformations. I'm planning to move on to another chapter and show you some further ideas in linear algebra. Okay, so there are still things to be done in like these linear transformations, but I will use our time to show you some more ideas. And I think the next week we will do something about eigenvalues and eigenvectors. Okay, so it's another important idea. Okay, what do you think? Do you have any questions about any of this material? I hope you like it. Any questions? No? How does the standard matrix help us? I didn't say it, right? I didn't say anything about it. So the standard matrix, I mean, I said things about it. So standard matrix basically, so it makes this computation easy, right? So to compute the L of something, you just multiply that something by A. So that's that gives an easy way, and it also makes this relation between matrices, determinants, and linear transformations. So linear transformations, in a sense, are just matrices. I mean, every linear transformation has a matrix representation. I talked about this yesterday, so it's basically saying is, so they can be represented by matrices, basically. Okay, so let me just say one thing about how can you use it. For example, once you find a standard matrix representation like this, you can, for example, easily compute, I don't know, like, so L of something, right? Just take the product with this matrix. Yeah, that's all I can say for now. So yeah, I mean, we won't be using, we won't need standard matrix representation, but it's important that you know the idea. So it's important that the linear transformations has matrix representations. That's the important thing that I would like you to know about the standard matrix representation. Okay, so our time is up. Okay, thanks for coming, and see you next week. Bye, everybody. See you.